Today's recording is also a great review of all of the gas laws we've learned so far. This video features the combined gas law. It's the last of the gas laws that we'll be covering in this unit. Our essential question for today is, what is the combined gas law, and how is it set up to solve a gas law problem? In this lesson, you will learn where the combined gas law comes from and how to write it, how the combined gas law is different from the ideal gas law, how to know when to use the combined gas law instead of the ideal gas law, and tips for setting up and solving problems with the combined gas law. So far, we've covered 5 different gas laws, and we started with what I call the individual gas laws. And those are the laws that compare 2 variables at a time. We started with Boyle's law, and this looks at the inverse relationship between pressure and volume. This law assumes that the container is closed, so we don't see N, the number of particles, and the temperature is constant. So that's not part of the equation either. Only the pressure and volume are changing. So you notice we have one set of pressure and volume conditions before and a different set of conditions after. Next was Charles' law, and this is the direct relationship between volume and temperature. Similar to Boyle's law, the container is closed, so no N. However, this time volume and temperature are changing from before and after, while pressure stays the same. The next individual gas law was Gay-Lussac's. It allows us to study the direct relationship between pressure and temperature as they undergo change, while volume remains constant and we're still in a closed container. The last individual gas law that we looked at was Avogadro's law. And this is the only individual gas law that can take place in an open container. The fact that N, the number of particles, can change means there has to be an opening which allows the addition or removal of gas particles. Here, the volume and moles of particles are directly related. They have before and after conditions, and pressure and temperature stay the same, so we don't see those variables in the equation. Finally, we put it all together in the ideal gas law. And the ideal gas law differs from the individual gas laws because it doesn't change or calculate changes in conditions. So in other words, we don't see any P1 or P2, we just see pressure and volume and N, and then R, the ideal gas law constant, and temperature. This law simply looks at a single situation and allows you to calculate the value of any one variable, let's say pressure, as long as we know the values of all the rest. So we would need to know what V is, and we always know R because it's a constant, and temperature. It looks like a lot to learn, especially since we're adding one more gas law to the collection today. The good news is that we really only need to learn 1, maybe 2 gas laws, and the rest can easily be derived from it. Even better news is that you've already learned the most important gas law, the one that you really need to remember, and that's the ideal gas law. PV equals nRT, or PIV-NERT. Sometimes helps you to remember what the letters are in the order that they go in. We're going to use a problem to demonstrate the versatility of the ideal gas law and how it can be transformed into the combined gas law, which is today's focus. And Shrek is going to be our inspiration for this problem. All right, so Shrek and Fiona are expelling a gas into the mud pit, starting out at body temperature, and then the mud pit is warm. So that small closed container of gas called a gas bubble is heating up, and we're going to explore the difference in the temperature. So as I read the problem, take note of which variables are mentioned and how this problem is different from the ideal gas law problems that you did in the last lesson. So sitting in his hot mud pit, Shrek expels a gas that takes up a volume of 17 liters at a pressure of 0.8 atmospheres and a temperature of 21.2 degrees Celsius. If the temperature is raised to 80 degrees Celsius and the pressure is lowered to 0.362 atmospheres, what is the new volume of the stinky gas? Let's look at the problem again. This time I've color-coded it so we can easily identify the variables that were measured together. There appears to be two sets of numbers for some of the variables, so change is taking place. Okay, so these red ones were all measured together. R is a constant, so we were able to throw that in. And all of the blue numbers were measured together. So we see those on the right side of the table. There appears to be two sets of numbers for some of the variables, so we know a change is taking place. That was happening with the individual gas laws, but none of the individual gas laws will help us here because at least on this side we have three variables that we're comparing to get a fourth, and over here we have two variables, but we have two unknowns. So let's think about PivNert. Could we solve both problems with PivNert? Well, the one on the left we definitely could because we know all the values except for one, and that's n. The one on the right, though, is a little trickier. We couldn't necessarily solve this one with PivNert because we don't know the value for n, and v is the one that we're asked to solve for. Fortunately, though, since the problem doesn't mention the number of particles, and since we know that the particles are contained in bubbles of gas, we have the same closed container. So the number of particles isn't changing here. So whatever n is under the beginning conditions, it'll be equal to n under the final conditions. So n is not changing. In other words, the container is closed, and since the red and blue n's equal the same number, and the red and blue r's also equal the same number, we can make them the same color on both sides. Now that we have values for everything in the PV equals nRT equation for the before and after conditions, we can solve for the variables that are the same in both problems, R and N. And we do this by dividing both sides by T. We want to get N and R together on the same side without anything else. So let's divide by T, and T will cancel, leaving us with N and R on the same side of the equation, and we've moved T to the left side. Since we have two problems, we can use the same arrangement of variables for both. So the red PV over T is equal to the same NR as the blue PV over T. And Shrek, being the math genius that he is, has an idea for the next step. Let's turn it into one problem. So we know that if both sets of variables are equal to the same thing, those variables are equal to each other. Whenever variables remain equal to each other before and after the change in conditions, they become part of the constant. So in other words, we can think of those as canceling each other out. Now that we're ready to solve the problem, let's check to see whether we have to do any unit conversions. So let's start with pressure. Both of them are in atmospheres, so that's good. We know that volume is in liters, and so our answer will be in liters. But the temperatures need a little bit of work. They have to be in kelvins, and they were given to us in degrees Celsius. So what I did here was added 273 to both of the temperatures so that we now have the temperature in kelvins. All right, we finally have arrived at the combined gas law. Since it isn't always practical to color code the variables, it's common practice to write the letters for each set of conditions with a different numbered subscript to keep them straight. So instead of red, we've got ones as subscripts over here, and instead of blue, we have twos as subscripts over here. Again, where did this come from? From rearranging the ideal gas law. And how do we know when to use the combined gas law? Whenever we've got the gas in the same closed container and two sets of conditions. All right, one of the things that can be intimidating about solving combined gas law problems is having temperature in the denominator on both sides. So a good tip for taking temperature out of the denominator is to cross multiply. Now we have an equation where there's nothing in the denominator. Another thing that can be intimidating is all the numbers in the problem. How do you know which P, V, and T are P1, V1, and T1? And how do you know which ones are P2, V2, and T2? When we're listing the variables, what we want to do is make sure that all the variables with a 1 subscript were measured together. And we can see in the problem that these were all measured together. And then all of the variables with a 2 were measured together as well. It really doesn't matter which ones are the 1s and which ones are the 2s. What matters is that they were measured at the same time. Okay, finally, we can solve this problem. We've identified that it's a combined gas law problem because we began by writing our variables and the numbers that we know for each variable. And we can see pressure, volume, and temperature. There was no mention of number of particles. So even though this is based on Pivnert, R is a constant. So R canceled and N canceled. And we just have 3 variables to compare. We can't use any of the individual laws because we don't have a single pair of variables that need to be shared. So the next step is to write the combined gas law. Notice I've already written it here with T out of the denominator. It'll make it easier for us to proceed. And the next step then is to solve it for V2 because that's the variable we want to know. So basically all I did was I divided both sides by P2 and T1, and that leaves V2 by itself. And then the last step is to plug in the numbers. Once we solve for V2, the calculator, of course, has more than 2 digits, but as we look at our data, 3 sig figs, 2 sig figs, 3, 3, 3. Since volume only has 2 significant figures, we rounded it to 2 sig figs and got 26 liters for our answer. All right, it's time for you now to practice a little bit with the combined gas law.